Hi everyone, my name is Hristo Chipiuski and I'm currently a postdoctoral fellow within NCAR's Advanced Study Program. In today's talk, I'll present some of the research I have been doing recently, and in particular show you how standard data assimilation methods used in operational Earth system models can be generalized such that they can work with arbitrarily non-Gaussian distributions. But first of all, I wanted to thank all these people listed here for the many fruitful and inspirational discussions that greatly benefited this research. I'm especially grateful to my postdoc mentors at NCAR, Jeff and Mocha, who have encouraged and supported me in various ways so far. I would like to start off this discussion, but first developing a fully probabilistic approach to estimation theory and demonstrate to you how this approach offers much more flexible mathematical tools for deriving new data assimilation algorithms. A natural way to motivate the need for such an approach is to first comment on the classical moment-based treatment. As you already know, the main goal there is to find the conditional means and covariances of the underlying state distributions. However, such an analysis is only suitable for the simplest possible case of Gaussian linear dynamics when the mean and the covariances provide a complete description of the state uncertainties. Unfortunately, our models and observations become ever so more complex, which means that the standard moment-based approach is no longer adequate. And as recently pointed out by this paper by Dan Christian and Michael Gill, we ultimately need to derive an alternative estimation framework which provides a complete description of the conditional state distributions. One possible way to formulate such an estimation framework is to use the tools behind probabilistic graphical models, such as the hidden Markov model depicted here, which represents a special instance of a directed acyclic graph. One of the benefits of such models is that it's very straightforward to visualize the conditional dependencies between random variables. For instance, with the hidden Markov model depicted here, we can decompose the joint distribution of x and y as a much simpler product, which involves the conditional densities in green and brown that are also represented by the arrows in the schematic here. However, the main reason why this representation of the estimation problem is useful for us is that state space models, which are the bedrock behind estimation theory, can be directly incorporated into them. To be a little bit more precise, the two conditional densities that you saw on the previous slide can be thought of as two densities that are induced by the state and observation equations in our state space model. In the most general case, these two functions f sub k and g sub k are some unknown nonlinear functions, but it is pretty standard practice in estimation theory to assume that the model and observation noises, represented by the epsilon here, are additive and Gaussian distributed, which leads to this more familiar looking form of the classical state space model. Now, it's important to highlight here that unlike more traditional formulations of this model, I make a clear distinction between random and deterministic variables by writing them in upper and lowercase letters. And this distinction between random and deterministic variables is vital for our mathematical analysis of this additive Gaussian state space model. For instance, it leads to the important conclusion that all the conditional densities in the state space model are Gaussian, regardless of how we choose the state and observation functions m and h. However, despite this Gaussian structure of the hidden Markov model, it turns out that closed form solutions can be only obtained only if the functions m and h are further restricted to be linear operators. This property is certainly quite discouraging and has been one of the main reasons why research in the last 10 to 15 years has targeted the development of particle-based data assimilation alternatives. Fortunately for us, though, not all hope is lost, and so in the next section, I'll show you how we can actually reformulate this state space model so that we can obtain exact solutions even in highly nonlinear, non-Gaussian setups. The main inspiration and ideas for this new estimation theory comes from a subfield of machine learning known as invertible neural networks, which are a special network design where all functions belong to the class of diffeomorphisms, which are invertible, differentiable functions with differentiable inverses. Now, the key insight for us is that these special functions can be used to construct more interesting non-Gaussian distributions. And here is how this might work out. Suppose that we start with some simpler base distribution, such as this bivariate Gaussian, and then we apply a series of nonlinear transformations until we arrive at a more interesting distribution in the final figure, which may be more representative of the data that we're trying to approximate. Now, how can we use this guiding principle in the context of estimation theory? Well, starting from the general form of the state space equations, we can actually make the following two assumptions. First of all, we can restrict the functions f and g, which are the state and observation functions, to be some nonlinear diffeomorphisms, which are parameterized by the vectors theta f and theta g. And second, we can assume that the input to these functions, instead of coming from some being arbitrary, that they actually come from an auxiliary linear Gaussian state space model, to eventually lead to this new form of the state space model, which has a structure that resembles the invertible neural network structure we discussed earlier. The main theoretical result that I wanted to share with you today relates to the filtering distribution under this new state space model, which, as you can see here, is given by some Gaussian distribution, which is pushed forward by the state function f sub k at the current time step k. The analytical tractability of this finding is quite encouraging given the widespread perception in our community that exact estimation is not possible beyond the simplest Gaussian setting. But there are two additional properties that I wanted to briefly mention here. The first one is that if we take the nonlinear f and g functions to be the identity transformation at each filtering time step k, then the two recursion relationships that you see at the bottom of this theorem actually recover the common filter recursions. So in other words, the common filter is nothing more than just a special case of this more general nonlinear filtering theory. Another property that is closely related to the common filter is that at each filtering time, the prior distribution is conjugate to the likelihood function, regardless of how the observation function g sub k is chosen, which has the practical importance of preserving the dynamical balances after the data assimilation update step. So how can we use this new filtering theory in the context of high-dimensional problems? Well, analogous to the way in which the ensemble common filter approximates the exact common filter recursions, we can similarly construct an ensemble update that converges to the analytically tractable non-Gaussian posterior. And we'll refer to this new method as the ensemble conjugate transform filter. To demonstrate how this new approach works, we'll consider a very simple numerical example in which the prior comes from this bivariate non-Gaussian distribution, which has a non-negative x1 component and a doubly bounded x2 component. We'll further suppose that we only observe the first component of the state and that this value is very close to the physical bound of the x1 and also has a very small observation uncertainty as given by the peak nature of the likelihood function. On this next slide, we can see that simulation with a standard ensemble common filter produces a highly biased solution that not only is farther away from the true posterior PDF, but it also contains a high number of ensemble members that violate the physical bound. On the other hand, simulation with the newly introduced ensemble conjugate transform filter produces an analysis update that approximates exactly the true Bayesian posterior. This is all I had for you today. In interest of time, I will stop here and leave the summary slide on display while answering some of your questions. Thank you very much.